2.4, the chain rule. So far, the tools that we have for differentiating functions work on some of the basic functions we've been given and the polynomials we've been given. The chain rule, however, makes it a lot easier to do more complicated functions, such as functions that we can look at that are composite functions. A composite function is a function that's built of two different functions. So first we'll give a definition of a composite function so that we can get some context here. A composite function that is any function f of x that is equal to, and we're going to write this two different ways, but remember you have g of h of x. We've seen it written that way, where this should be a hollow circle, right? Okay. Another way that we've written that is just putting h of x inside g of x for x. Okay, so in this situation where you have a composite function, you're putting x into one function and then that function into another function.
It's only one type of composite function, though.
Yeah.
That we explored, I noticed.
Okay, in these functions, you have what we're going to describe as an inner function and an outer function. So in this notation, it's pretty easy to see. H of x is the inner function, and g of x is the outer function. And we can apply that here as well. If you have g of h of x, h is the inner function, and g is the outer function. So the chain rule is a really efficient way of differentiating composite functions. The first thing we're going to do is differentiate the outer function, g of x, with respect to the inner function. Then multiply the derivative of the inner function. That's going to make more sense after we do a couple. So here's the chain rule definition. The chain rule says, given two differentiable functions, g of x and h of x, the derivative of the composite function, I'm going to do this on two lines actually, the derivative of the composite function f of x, which equals g of h of x. So if you have f of x and it is a composite function of g of h of x, you can see that it's actually two functions. The derivative is f prime of x. So the derivative of f of x is this. We take the derivative of the outer function, so the derivative of g of x, but with respect to h of x. That'll make more sense after you see an example. Basically, you don't touch what's inside. You just differentiate the outside, and then you multiply it by the derivative of the inner function. Okay, I'm going to leave that up there, and we're going to head to example 1. Example 1. We are going to differentiate f of x equals 3x minus 5, close bracket, to the power of 4. So if we're looking at this, we can see that it's a composite function. It can be built of two functions. One of the functions is 3x minus 5. That would be our inner function. And one of our functions is x to the power of 4. So x to the power of 4 is the outer function. That's what's happening to the inner function. Okay, so let's just jot down a couple notes for what we know. I'm going to leave f of x there, and we're going to introduce, or we're going to say f of x is the equal to g of h of x. Okay, it's a composite function. What is the outer function, g of x? It's x to the power of 4. And the inner function, h of x, is 3x minus 5. When we're differentiating this, again, we're going to do it slowly, step by step. When you do it in your practice problems, by that time, you'll probably be a little bit more proficient. But what I'm going to do right away is just take the derivative of g of x and h of x right away. So g prime of x then is 4x to the power of 3. And h prime of x is 3. What does that tell us? Well, let's write down our chain rule. F prime of x, the derivative of f of x, is equal to the derivative of the outside function with respect to the inside function. It just means pretend this whole thing is x, if that makes sense. And then we're going to multiply that by the derivative of h of x. So now all I need to do is sub in what I know. If the derivative of g of x is 4x cubed, but I have g prime of h of x, that means wherever I have in this derivative of g of x, I have 4x cubed. Wherever I see an x, I'm going to put h of x in there. Okay, h of x is 3x minus 5, and it's cubed, times the derivative of h of x, which is 3. Okay, just taking a brief look at what we did. What did we do? We started with f of x, which is 3x minus 5 to the power of 4. All we did was leave 3x minus 5 there and take the derivative of the outer function. We put a 4 in front, and now it's raised to the power of 3. And then we're going to multiply by the derivative of what's inside, which is just 3. Yes? Good? Not so bad so far. When we do this, we don't need to fully expand this binomial cubed, okay? But since multiplication is commutative, we have 4 times this thing times 3. We can simplify this to be 12 times 3x minus 5 to the power of 3. And that is f prime of x. Example 1b, f of x equals the square root of 4 minus x squared. Okay, right away we can see that this is a composite function. I'm going to do it the same way this time. F of x is g of h of x. So I can identify my outer and my inner function. G of x is our outer function, and that's going to be the square root symbol, which is the square root of x, or for our convenience, x to the power of 1/2. The inner function, h of x, is 4 minus x squared. Okay, take the derivative of g of x, we get 1/2 times x to the power of negative 1/2. And we're going to leave it like that for now. And if we take the derivative of h of x, we get negative 2x. So that part should be pretty straightforward. Now when we take the derivative, f of x, I'm going to copy down our chain rule. We're taking the derivative of the outer function with respect to the inner function times the derivative of the inner function. That's going to leave us with 1/2, and then h of x, the inner function, stays in place of x. So that's 4 minus x squared to the power of negative 1/2. And then we're going to multiply that by the derivative of h of x, h prime of x, which is negative 2x. Okay, I've put brackets around this just to kind of, in my mind, keep it together. What I could do is I could just take out that multiplication sign and squeeze it together a bit more, but just leaving it in there so we can see what's happening. And now we are expanding. So it looks ugly and clumsy with these fractions and this negative and all that, but since multiplication is commutative, I can just multiply negative 2x times 1/2, and that's just going to give me negative x out front. And we'll do this in 2 steps, but this bracket is going to stay the same to the power of negative 1/2, which is, in order to express as a positive exponent, I would need to bump this whole piece, this whole factor, into the denominator, and at the same time I'm also going to convert my to the power of 1/2 into a square root. So the last step here looks like this. We've got in the numerator negative x, in the denominator the square root of 4 minus x squared. And just briefly before moving on, you might see this in different notation. You might see this as, remember, the derivative f prime of x could be written dy by dx, in which case we would let these two functions be maybe the function y and the function u or something like that, or the function u and the function w, because I'm already using the letter y to be our original function. But we could do it in different notation. We would let w be the square root of u and let u be 4 minus x squared. So now we took our inner function and called it u. We took our outer function and said it's going to be the square root of our inner function. In that case, finding the derivative, we would again need the derivative of both of these functions, which would be dw by du. And we differentiated it already, but it would be 1/2 of u to the power of negative 1/2. And this actually is really easy to see now that we're going to leave u in there, this inner function unchanged. And du by dx is negative 2x, just like we had before. And then you follow in by doing the product of both of these. So then dy by dx, so the derivative of the original function, is equal to dw over du, which is the derivative of the outer function with respect to the inner function, times du by dx, which is the derivative of the inner function, and then it would work out just like we see here. What would we say? This is just different notation, or this was Leibniz notation or form. Same thing, different notation, helpful in different circumstances. Okay, video watchers, slight change in what we wrote. We replaced all our w's with y's, so that it says that the derivative of y with respect to x is equal to y with respect to u times u with respect to x which is the derivative of the outer function with respect to the inner function, times the derivative of the inner function with respect to x, which is exactly what we actually did. I didn't need to change that to a different letter. So example 2, we're just going to differentiate a few more using this new notation. So we have y, there's two of them, there's a and b. If we have y equals negative the square root of u, where y is now a defined function and u is also a function, so here's u, and u equals 4x cubed minus 3x squared plus 1, we need to find dy by dx. Find dy by dx. So same thing is going to happen here. We're going to first find dy by du, which is the derivative of the function y with respect to u. First, what's easiest is probably to take y and express it the square root as a exponent of 1/2. Then we can see that the derivative, and I'm going to just change my color here, the derivative dy by du is negative 1/2 u to the power of negative 1/2, and the derivative du by dx is 12x squared minus 6x. So according to the chain rule, dy by dx is equal to the product of dy by du and du by dx. So we'll sub those things in. The derivative of y with respect to u is negative 1/2 u to the power of negative 1/2. The derivative of u with respect to x is 12x squared minus 6x. And at this point, we could probably stop putting that multiplication symbol in between. We know it's being multiplied. Okay, because we want to express this in terms of x, at this point we're going to take this u and we're going to replace u with what it actually equals. So with the function that it is, which is right here. So we've got negative 1/2 times 4x cubed minus 3x squared plus 1 to the power of negative 1/2 times 12x squared minus 6x. And then we're not going to expand this whole thing. We're going to simply take this portion, this factor, 4x cubed minus 3x squared plus 1 to the power of negative 1/2. We're going to move it into the denominator and express it as a radical instead of exponent to the power of 1/2. We're also going to take this 2 into the denominator where it is. So in the numerator, we are left with negative 12x squared minus 6x, which is just this positive factor here. And that's actually wrong because this negative sign needs to get distributed to both of its terms. So this sign is actually plus 6. It changes the sign of positive 12 to negative 12, and changes the sign of negative 6 to positive 6. And then in the denominator, we have the square root of 4x cubed minus 3x squared plus 1. Oh, and our, don't let me forget, our 2 out front, because it's half 1 over 2, so we still need 1 over 2. Yes? 2b, we have y equals u to the power of negative 3, and u equals 2x minus x cubed, and we're asked to determine dy by dx at x equals 2. Let's talk about what that means for a second. So we're going to differentiate it, but then we're also going to find the value of our differentiated function of the derivative at x equals 2. So remember, the derivative corresponds to the slope of the curve at any point, and we're going to be finding the slope or velocity at x equals 2. So first step, we're going to kind of ignore this x equals 2 part, and we're just going to differentiate this the same way that we did before. So if this is y, then dy, this is y with respect to u. So the rate of change of y with respect to the rate of change of u is negative 3u to the power of negative 4. Be really careful with this. Common mistake would be to say, oh, it's negative 3u to the power of negative 2, but that would actually be increasing your exponent rather than decreasing it 1. And we have u with respect to x, so the derivative of u with respect to x is going to be 2 minus 3x squared. According to the chain rule, dy by dx is equal to dy by du, the derivative of the outer function with respect to the inner function, times du by dx, the derivative of the inner function. Sub in what we know. We've got negative 3 times u to the power of negative 4, and then in brackets we've got 2 minus 3x squared. In this case, our brains have the tendency to keep all this grouped together, but we can actually view this as different factors, right? We have a numeric factor and a variable factor and then a grouped factor. And this negative 3 is just as attached to this group as it is to the u to the power of negative 4. And we see a negative exponent, so this guy is the only one that's going to get bumped into the denominator. So we can wrap up this step by putting u to the power of 4 as a positive exponent in the denominator. And then in the numerator we have negative 3 times 2 minus 3x squared. And we could expand that, but it's not necessary to expand it completely, because all we need to do is throw in x equals 2 wherever we see an x. So if we're going to go for our next step, we're taking our derived function, dy by dx, and we're finding its value where x equals 2. So I'm going to copy it down, and everywhere I see an x, we're going to put in x equals 2. And also we're going to sub in the function u. Maybe we should find that first. Maybe we'll do that off to the side. But I'm going to we're going to leave our denominator for a second. So our numerator is negative 3 times, in brackets, 2 minus 3 times 2 squared. And then in our denominator, we're putting in u to the power of 4. So I want to do a little bit of side work. I'm going to take u, which equals 2x minus x to the power of 3. And we're subbing in 2, so u with respect to 2 is 2 times 2 minus x to the power of 3, which is 2 to the power of 3. That gives us 4 minus 8, which is negative 4. So our denominator then is negative 4 to the power of 4. So I'm just going to draw us a little bit of an arrow here so we can see what we're doing here. This u, we're working with it here, and we're subbing it back in here. The numerator can simplify. We have 2 squared, which is 4, times 3 is 12. So we've got 10 minus 12, sorry, 2 minus 12, which is negative 10, times negative 3, which is positive 30. And negative 4 to the power of 4.
Wait, why do we sub in negative 4 there again?
And 4 to the power of 4, I know it's going to be positive because it has 4 positive factors. That is 256. Both of these are even numbers, so this can reduce at least that they're both divisible by 2 to 15 over 128. What did we do? We took the derivative of dy by dx of this composite function, which was built of the function y and the function u, and then we found out what the derivative was at x equals 2. A little bit of a tricky part here with u to the power of 4. We just took it out and did the work on the side and put u back in, still to the power of 4, and then simplified it out. So this is the rate of change of the function, composite function, at x equals 2. Okay, that example was a special case of the chain rule. It occurs when the outer function is a power function. So the outer function here, y, was a power function. And the derivative consisted of using the power rule first. I think just doing this is the power rule. So a note on power of a function rule. Power of a function rule says that if y equals u to the power of n, so if y is a power function and u is g of x, any function, then the derivative with respect to x of the function that we're given, which is u to the power of n. So basically what this is saying is if you have a function and it's a polynomial or another function raised to the power of something, then it's a composite function with an inner function that could be anything and an outer function that is an exponent. Okay? Then what do? We simply take the power law, which is taking n down in front as a multiplier and dropping the exponent by 1. So that notation looks like this. N u to the power of n minus 1. That's familiar. Times the derivative of the inner function with respect to x. So times du by dx. Okay, another way to write that. So again, this isn't super new. This is just depending on what this outer function is, this is how you differentiate it if it's a power function. You use the power function rule. Okay. Another way to write that is, so we're taking the derivative d by dx of g of x, which is a function raised to the power of something else. So exactly the same. You just have some function and it's inside another function, which is a power function. So some polynomial or some function raised to the power of some number. And then what is the derivative? The derivative is you take that value n, you put it out front as a multiplier, and then you drop the exponent by 1, and then you multiply it by the derivative of the inner function. Okay, so again, this is nothing new. It's just a different way of writing this specific case where the outer function is a power function. So example 3, we're applying that power function rule and combining it with the product with the chain rule. Example 3, we've got, we're determining the equation to a tangent. So there's another step in there. Equation of the tangent to f of x equals 3x times 1 minus x squared. So there's our curve, and we're finding the tangent at x equals 0.5. So first thing we do is differentiate the function. We're going to first apply the product rule and then the power of a function rule. So if this is f of x, then f prime of x is, we're going to copy down this second function. We're not going to change the second function. So that is the product rule first. The product rule says take the derivative of the first function and multiply it by the second function, and then add the derivative of the second function times the first function. Okay, so that's the product law. I'll write it. Product law says take the derivative of the first function, which is d by dx of 3x, put that in bracket, multiply it by the second function, which is 1 minus x squared. Then we are going to take the first function, 3x, and multiply it by the derivative of the second function, 1 minus x squared. Your book puts this piece after this piece, probably just because if you write it this way, it looks like you might be taking the derivative of this whole thing, but you're not. You're just taking the derivative of that part and multiplying it by that. So they're probably right in the way that they write it. I should have written this bracket first and then the derivative of that, just like I did here. So it's separated by taking the derivative of that multiplication in between. Good, good. Carrying on. The derivative of this 3x is 3, multiplying by 1 minus x squared. Then we are multiplying, we have 3x times the derivative of this piece of the function. And here we're going to apply the power rule of the function, which says that we're going to take the derivative of the outer function, which is x squared, with respect to the inner function. So if the outer function is x squared, and then we have 2 times x, which is 1 minus x, and that's it. The exponent drops 1 to 1, and then we multiply that by the derivative of the inner function, which is negative 1. What did we do? This is the product rule, and this is the power of a function rule, or the chain rule. From here, we don't need to simplify this a whole lot further. We don't really need to do any more arithmetic on it. We can if we wanted to multiply this negative 1 by the 2, or also this is all just multiplication, 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 multiplication. We could make this negative 6x times 1 minus x. That might make it a little bit easier. But our book just keeps going as is. So now we're going to determine the slope at x equals 0.5. So we're taking the derivative, which we've just found. We're subbing in 0.5 for x. In the bracket here, we have 1 minus 0.5 squared. Then we have 3x, square bracket, 2, open bracket, 1 minus 0.5, close bracket, times negative 1, close bracket, close bracket. And you could probably punch that whole string into your calculator, or you could do it in 2 parts. The first part here, 0.5 squared times 3 ends up being 0.75. And, oh, I forgot to put in a negative 0.5 for the 3 times x, 3 times 0.5. That whole string becomes negative 1.5. So the slope at x equals 0.5 is negative 0.75. Okay, we have the slope. We're going for the equation of a tangent. So the next thing we need is a tangent point. So this is slope of tangent at x equals 2 is negative 0.75. Keep that information. Now we need our tangent point. Tangent point. A lot of review in these examples too. Tangent point, we are at an x value of 0.5, and we're just going to sub that into our original function to find the corresponding y coordinate. So f of 0.5 equals 3 times 0.5 times 1 minus 0.5 squared. So we've got 1.5 times 0.5 squared, which is 0.25. So you have 1.5 times 0.25, which is 0.375, or 3/8. So our tangent point is 0.5, 0.375. And now we're just using our point slope formula. Point slope formula. We've got y minus y1 equals m times x minus x1. Our point, our y coordinate is 0.375. Slope is negative 0.75. And our x coordinate is 0.5. Okay, I'm going to, on the right side, distribute negative 0.75 to both terms in the binomial. That gives us negative 0.75x plus 0.375. And then we're going to add 0.375 to both sides, which gives us y equals negative 0.75x plus 0.75. Ba-ba-da. Okay, this is the equation of the tangent to the curve at x equals 0.5. It looks something like this, and the tangent comes across like that. Example 4. Example 4 is a word problem that requires calculus and the use of the chain rule to solve. And we have a situation where Andrew and David are running a marathon. So they're both going to run the distance of a marathon, which is 22 miles or 26 miles or 42 kilometers. And they're both going to leave their houses at the same time. Andrew's house is 22 kilometers south of David's house. So I'm going to draw a diagram. It's there in the book as well. But we've got David's house, and then 22 kilometers south of that, we have Andrew's house. Andrew is going to run north at 9 kilometers per hour. So Andrew, I'm just going to add these things in color. Andrew is going to run north at 9 kilometers per hour. David is going to run west at 7 kilometers per hour. So David is running west at 7 kilometers per hour. Determine the rate of change of the distance between the two runners after 1 hour. So Andrew is going to work his way toward David's house, and David is moving away from his own house, but not linear. It's in a different direction. So as they do this, they're actually going to get closer and closer and closer together. But then at a certain point, as Andrew gets closer and closer to David's house, they're going to start getting further and further apart again, if that makes sense. Okay, so they kind of form a triangle. As soon as they each take one step, a triangle is formed. Okay, and that triangle is going to kind of bring them closer together and then further apart again. That's my prediction. I don't know if that's entirely true. But okay, the distance between them, let the distance between them be s of t. And the distance between them is obtained by using two formulas. We have distance, which equals velocity times time. And we have the Pythagorean theorem is going to help us. Pythagorean theorem. Okay, so Andrew runs at a speed of 9 kilometers per hour, which is velocity with respect to time. So he's running 9 kilometers per hour. That's a measurement of velocity. And he's going to do that for t hours. Okay, so Andrew, the distance that he covers is 9t. 9t. So Andrew is 9t. And since his house is 22 kilometers from David's house, which we were told in the problem, then the ground that he covers is 9t. Then the ground that he doesn't cover, or the ground that he is, the distance he still is away from David's house, is always going to be 22 minus 9t. Okay, so after 1 hour, he's covered 9 kilometers, and there's still 13 kilometers to go. After 2 hours, he's covered 18 kilometers. There's still 4 kilometers to go. And so maybe distance from David's house is 22 minus 9t. And David, David's distance is 7t. 7 kilometers every hour, and that's going to be away from his house. All right. So as he's running this way, David is running west. Andrew is running toward his house. The distance between them at any point, okay? Remember, this is a moving point. This point can move. At the beginning, it's way down here. And then as they keep running, it moves up and up and up, okay? So this isn't necessarily to scale, but what we have here is a right triangle where the distance of one leg is 22 minus 9t, and the distance of the other leg, the length of the other leg, is 7t, which makes the hypotenuse the square root of the sums of the squares of the two legs. We can write that. That's just Pythagorean theorem. C equals the square root of a squared plus b squared. Okay, that's just Pythagorean theorem. So into that, we're going to sub our two lengths. So we're going to take the distance from David's house to Andrew. That's going to be our first leg. That's going to be a. So that's 22 in brackets minus 9t squared. And then our second leg is 7t. And that gets squared. I put the whole thing in brackets. You have to remember to square the numerical part and the variable part. From here we can just simplify that square root into something a little bit more usable. The expansion of this, we're not going to show it, but it's a binomial squared, so you'd have 22 squared minus 2 times a times b plus b squared, if you remember that pattern. I could write it out. We'll go 22 squared minus 2 times 22 times negative 9t plus 9t squared. That's just that expansion there. And then we have plus 7t squared. This reduces to the square root of 130t squared minus 396t plus 484. Now, this measurement that we got, c squared, is the displacement between them. Okay, it's the distance between them, s of t. So this hypotenuse represents the distance between David and Andrew at any point during their run. Okay, so it's s of t. What we are asked to do is determine the rate of change of the distance between the two runners after 1 hour. So we are going to find the derivative of s of t and then sub in t equals 1 hour. So step 1 for finding the derivative of this is putting it into exponent form. So in brackets, we've got this whole polynomial. We're going to raise it to the power of 1/2. And now we're going to differentiate it. S prime of t. We're going to use the power of a function rule, which means that we're going to take the derivative of the outer function and then multiply it by the derivative of the inner function. So the outer function, we have an exponent of 1/2. That comes to be a multiplier. Copy down the inner function without changing anything. The exponent drops 1 to negative 1/2. And then we're going to multiply by the derivative of the inner function, which is 130 times 2t, which would be 260t, minus 396.
Wait, where do we get 260 from?
So you leave this multiplier out front, and you take the derivative of your variable, which is t squared. So the derivative of this is 2t.
Oh,
So
okay.
2t times 130 is 260t. All right, from here, we're just going to put this expression with our negative exponent in the denominator, and we're going to express it as a root again. So in the numerator, we're just left with 260t minus 396. The denominator is 2 times radical 130t squared minus 396t plus 484. And we don't need to simplify any further. We just need to sub in t equals 1. So the derivative of the displacement function at 1, we're just going to sub in 1 everywhere we see a t. So in the numerator, we have 260 times 1 minus 396. In the denominator, we have 2 times the square root of 130 times 1 squared minus 396 times 1 plus 484. And if you're careful in your calculator, that will eventually reduce to approximately negative 4.6. What does that tell us? It tells us that after 1 hour, the distance between Andrew and David is decreasing at a rate of 4.6 kilometers per hour. Therefore, the distance between David and Andrew is decreasing. I should say after 1 hour. The distance between David and Andrew after 1 hour is decreasing at 4.6 kilometers per hour. Dun da dun 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 dun. Okay. Situation where two guys were running. One was running toward the other person's house, and that guy was actually running away. He didn't want to run together. The distance between them is represented by the hypotenuse of this right-angled triangle, where one of the legs is the distance remaining on Andrew's run, who's running at 9 kilometers per hour. We used Pythagorean Theorem to get an expression for the distance between them, which again is this hypotenuse, which is always changing. And then the rate at which it is changing is its derivative. We used a couple of our new laws to get that. We simplified it as much as we needed to sub in t of 1 to show the rate of change at 1 hour. Did some basic arithmetic and found out that they were getting closer together at a rate of 4.6 kilometers per hour. Practice problems that you could be responsible for knowing come from page 117 is where it starts. And you could see anything from number 1 to 16 on an assignment or a test.